can correspond to two different kinds of trajectories. It can be quasi-periodic or it can be periodic. Periodic in the sense like I take 1, 2, 3 steps, and again, if I apply the same step again, I will come back to the first step and again start 1, 2, 3. So A, B, C, and come back to A. So it's a period 3 of it. Okay, period 3. So similarly, that one is a periodic trajectories. What are quasi-periodic trajectories? Quasi-periodic trajectories are something which are not periodic, but look almost like periodic. Okay, so they are known as quasi-periodic trajectories. So invariant closed curves can be of two types: periodic trajectories or yes, it will not come back. Suppose I will tell yes, sir has asked a nice question like if I have 2 points A and B, so this is point A and I have gone to point B. Again, if I apply the map F, I should come back to point A. That is known as the period 2 point. Now, what is quasi-periodic? If I am at point A, I go back to point B. Then, when I apply the map F, I don't exactly come back to point A, but near to point A.
That means the same as the pre-period.
Kind of. But in dynamical systems, we have some rotation number concepts. So it will have irrational rotation number. If you have irrational rotation number, you can say that it is a quasi-periodic orbit. If it has rational rotation number, you say it is periodic orbit.
If the equation never comes to any such point, then it is not there.
Yes, yes. So here I give a visual representation which I have done in MATLAB or Python you can see. So on an invariant closed curve, I have two types. They can be periodic or quasi-periodic invariant closed curve. So on the left side, you can see on the left, it is a period 6 orbit. Mind you, the blue triangles, count the number of blue triangles, they must be 6. Okay, those are stable. The stable one I have denoted in blue color. Period, and the saddle ones, like there is always two parts. There is a hero and there is a villain in any movie. So there will be a stable, there will be an unstable. Okay, so corresponding to stability, there will be always instability. So those instability you are seeing in black squares, and count the number of black squares, there will be also 6. Okay, they are lying in such a nice way that if you consider the one-dimensional unstable manifold, it's fine if you don't understand this, but it is some special curve, okay, one-dimensional curve. If you compute it, there are some methods to compute. If you compute it, then they nicely form a loop. And if they do, if you see such kind of structure to this, not all periodic orbit will give you this structure. If they give you structure like this, where you consider the unstable manifold, and they give you a loop, okay, then such kind of orbits are known as mode-locked orbits. Mode-locked periodic orbit. It is something stronger than a periodic orbit. That is mode-locked periodic orbit. That's exactly the aim of this orbit. Okay. RP you can see is the quasi-periodic orbit. Okay, so you can see the points. It is not a curve, mind you. It is looking like a curve. It is not a curve. If you zoom in, it will be a collection of points, million of points. But they are not coming at any one point again. If they come at any one point again, they will be periodic. Okay, so they are not coming back at any one point, rather close, plus epsilons nearby. So that if you consider long enough iteration, they will form like they will look like a curve, but it's not a curve. Okay, there are sets of points, million. Part C, you are seeing something more stronger, that is known as a higher dimensional quasi-periodic orbit. So B part you can see it looks like a curve, but C part is something higher dimension, that is a torus. Okay, so it is like a 3-dimensional or it has 3 different frequencies we see. So it's a higher dimensional torus. It is also a kind of quasi-periodic orbit. Okay. So this is just some visual interpretation what is going on, not just relying on theory. Okay. So coming back, the mode-locked periodic orbit which I just showed in computation. Okay. So this is just a schematic diagram for this. You can see 1, 2, 3, 4, 5, 6. How many blue triangles are there? How many black squares are there? 6. So every hero, every villain. Okay. So you can see the blue triangles are the stable ones. Means if you iterate your points again and again, it will go to that point. It will get attracted to that point. Whereas the black squares, they, if you go along that direction, they will move away. Okay, so that is known as a saddle. All right. So if you consider the red part, the unstable one-dimensional unstable manifold, they are unique. One-dimensional unstable manifolds are unique to each saddle point. If you consider the one-dimensional direction, one-dimensional unstable manifold, they will make this closed curve. Okay, they will make this closed curve. If you see a very nice closed curve like this, it is known as a saddle and a node connection. Node is also known as stable. So you can say it is a connection between a saddle and a stable. So stable we also call it as a node. So saddle and a node connection. Alright. So it's a mode of period 6 orbit and it is also an invariant closed curve. Okay. Next, let us look into another sort of diagram. This is known as a saddle focus connection. Okay. So here also you see how many blue triangles are there? 6. How many black squares are there? 6. So same villain, same heroes. Okay. But here some difference is there. Why such difference has happened? So the blue triangles you see is a stable period 6 orbit. Okay. So how we know about stability? I have not covered here, but through eigenvalues. It's a 3-dimensional map, so you will get the Jacobian matrix, a 3x3 matrix. And how many eigenvalues it will have? A 3x3 matrix will have how many eigenvalues? 3 eigenvalues. And depending on the 3 eigenvalues, you predict if it is stable or not. If all eigenvalues are less than 1 in absolute value, it is stable. Okay? So therefore, if the blue triangle you are seeing has developed complex conjugate eigenvalues, then it will develop a spiraling action here. I hope in differential equations, if some complex conjugate is there, you are always seeing some features in your phase space. So same thing here, okay? Loosely speaking. So the blue triangle here has developed some complex eigenvalues due to which the unstable manifold has developed some spiraling kind of action here. And this is known as a saddle focus connection. Saddle is our villain here. Focus is also a stable. Focus means it is spiraling in. Okay? But you can see how much it will spiral. That is a good question. How much it will spiral? You will see this is the stable point and it will be like this. If you zoom in after 100 more iteration, it will be nearby. How many you iterate, it will still not reach to the stable. So it is infinitely of many length. Okay, but the previous one, the slide is not moving. Remember the previous slide I draw, it is like this circle, right? So it has a finite length. You can find it. But this figure doesn't have a finite length. Why? It spirals. It spirals near the blue triangle. So the saddle node connection and these structures are not homeomorphic. Okay, homeomorphic means what? You must have seen like a donut, a coffee cup you can just squeeze in and make it into a donut. That's like a homeomorphic. Okay, so this one you cannot do because this one you cannot do because it is of infinite length. Therefore, those two structures are not homeomorphic. This structure and this structure are not homeomorphic. This is a property. Okay? Now, some of the previous research work in this field, in 1983, a Japanese scientist named Kaneko have observed doubling bifurcation of possibility orbits. Okay, you saw that possibility orbit is like a circle, like a loop. Okay, so doubling of that occurs. What is doubling of that? Means in higher dimensional. And later, after he found out, researchers found in many experimental systems like radiophysical system, hyperimpedance systems, and many more. In 2012, Sumitro Banerjee discovered that local bifurcations of possibility orbit can occur. That means forward. So yes, so in the picture you can see on the leftmost picture, the red dots you see is the previous one it was existing. But as you vary some parameter in your system, like just like an AC remote. You press something and the temperature increases. Just like that, one variable will be there in your system. You will see in Excel. Okay, if you vary the red dots, it is like a possibility orbit, previously stable, previously stable. When you vary the parameter, it got separated into two loops. You saw that? First A figure you see. So the red dots is a quasi-periodic orbit, previously stable, therefore it is shown in red. Now as you vary the parameters, it got separated into two loops. It's separated into two loops. You can see two black loops, but disjoint. They're disjoint. Okay, that is a doubling bifurcation. One type of doubling bifurcation, known as disjoint doubling bifurcation. Okay? But the part B you see is a red closed invariant curve. But what happens to that? If you vary the parameters, it doubles in length. Not exactly strongly doubles in length, but somehow the length has increased. Okay, but it has a special shape that it lies on a Mobius strip. It lies on a Mobius strip. Okay, so therefore we are interested in these two bifurcations. Okay, the other two bifurcations C and D you are seeing are the bifurcation into higher dimensional torus. Okay, like a closed invariant curve bifurcated into a torus. And the third part, you will see D part is like stable and unstable, they come closer, collide and annihilate. Okay? But we are not interested in this talk for C and D, but I am showing that they exist. We are interested mainly in part A and B, okay? And I will show you the real examples. Okay? Fine. So research question, what is the question? Okay, so this is the research done so far, but what are the research questions we are trying to address? That's how you start research. Okay? You do read some papers and see where are we lacking, where are they lacking, what can be done, and then you frame some questions, try to tackle it. If you are successful in that, yes, you can write your findings and send to some journals, appropriate journals, and then yes, they give you comments and it will get published. That's the idea. So this is the research question we are trying to address. The above lines concerns bifurcation of quasi-periodic orbits so far. Whatever I have shown you is all about quasi-periodic orbits. Okay. However, the mode-lock periodic orbits, the villain and hero you saw, the collection of them and a loop, represent a generic case. And by the first page of my slide, I will show you such orbits. Actually, such mode-lock orbits cover a large range in your parameter space. Then a quasi-periodic orbit. What is my proof? I will just give you a visual proof. Yes, the background of the slide. The background of the slide denotes the region where the mode-lock periodic orbits exist. If it is a period 2 orbit, I have colored green. If it is a period 6 orbit or 4 orbit, I have colored pink. Okay, it is computation. If it is period 8 orbit, I have colored blue, like that. So you can see in this region, they are mostly occupied by mode-lock orbits. Okay, so why not someone has done research on mode-lock orbits? Okay, fine. So yes. So now you can see why I am telling you that such mode-lock orbits occupy a larger range of parameters than the quasi-periodic orbit. Okay. This motivates us. All right. This motivates us to explore the ways in which mode-lock periodic orbit has bifurcated. Okay. So far you have seen bifurcations of quasi-periodic orbit, but how we can understand bifurcations of mode-lock periodic orbits? Okay. So although much research has been done on the doubling of quasi-periodic orbits, almost no attention was given to bifurcation of mode-lock periodic orbits. That's where we come in. That's where the talk is. So where this question has arisen, Gardini and Shushko are prominent scientists in this field, and they met at a conference in Italy in 2012, and they were discussing over a cup of tea that this is the talk, and they framed a conjecture on mode-lock orbits. Can mode, like quasi-periodic orbits you have seen, that they get disjointed, two loops, and one is the length doubled on Mobius strip. Okay, there are two types. There were two types. Now that is for quasi-periodic orbit. Now the question is, can the same structure be obtained in mode-lock orbits? That's a good question. So far, no one has answered the question in positive way. Okay. So that is the conjecture. So Gardini and Shushko, what they did in the conference, they said maybe it can occur, and they draw some geometric figures saying that yes, this is the conjecture. If like we don't know if it is true or not. Okay, that is what a conjecture is. You don't know whether it is true or false. Okay. So And so far, to support that conjecture or not to support that conjecture or falsify the conjecture, no examples were given so far in the literature till 2023. Till 2023. So, okay. However, to date, sorry, it's not visible, but I will read. However, to date, these conjecture have not been testified using some explicit examples so far in the literature. Okay. So this is the diagram we have discussed. Like it can happen, might happen, but we are not sure. So remember, this is the mode of period 3 orbit on the left, and 3 black dots, 3 black squares, and 3 blue triangles are there. And as usual, there is a loop. That is the one-dimensional unstable manifold. That is a saddle node connection, as per my previous slides. Okay, I hope you understand. Now we are concerned about bifurcation of those structures. So according to the 2012 paper which I just shown, it can bifurcate into disjoint, or it can bifurcate into a Mobius strip. Okay, double Mobius strip. That's exactly what is shown here. The top part you can see it is doubled and it is lying on the boundary of the Mobius strip. Okay. Now can you count? Don't count the inside one, but you can count 1, 2, 3, 4, 5, 6. 6 black squares and 6 black triangles are there in the picture. Okay. And on the below part you can see they have separated into two cylinder kind of objects, like two loops, okay, in 3D space, and they are lying on the boundary of the cylinder, gamma 2A and gamma 2B. Whereas the dotted ones are the unstable ones. They were stable before. As I varied the parameters, they have doubled. Okay. The question now is, this is the structure or this is the conjecture obtained so far, but can we observe this in some example? Is this possible even? To start for, we have to, there is no other way just but to do some numerical explorations. Okay. So this is the conjecture. It was conjectured by Laura Gardini and Shishko in 2012. That depending on, there will be 3 eigenvalues. You already know it's a 3-dimensional map. So first eigenvalue, second eigenvalue, third eigenvalue. Something must be happening in these 3 eigenvalues. Okay, to give us the structure. Okay. So they conjectured, not a theorem. They conjectured that depending on the sign of the third eigenvalue, the bifurcation can be classified into 2 types. The first type you can see is the length of the mode of orbit lying on a boundary of a Mobius strip. The B part is disjoint to the mode of orbit. The same structure as before I want to show. This is the top part is the Mobius strip doubled. The below part is the disjoint doubling lying on the boundary of the strip. Right, this is the conjecture. More about this conjecture, such kind of bifurcation, such kind of things, what I have told 2 types, can be observed in 3 or more dimensions. They cannot be observed in less than that. Due to the topology. Cylinder you can observe only in 3D. You cannot observe in 2D. Similarly, Mobius strip in 3D. Okay, so minimum dimension for this bifurcation is 3. So this is the conjecture. Consider a 3-dimensional map. You will have 3 eigenvalues, lambda 1, lambda 2, and lambda 3. So maybe this is a conjecture, just a rough idea. Lambda 1 may be responsible to create the saddle node connection. That is the, bounding the heroes and villains. Okay, that is a close draw. Lambda 2 eigenvalue can be responsible for the doubling. That it can double into a Mobius strip or it can double into a disjoint loop. Okay. Lambda 3 defines which kind of structure it can be. It is a conjecture, so they thought if lambda 3 is less than 0, it might be a length doubled Mobius strip. Okay. If lambda 3 is greater than 0, then you might see the disjoint loop. Okay. Why in such case lambda 3 less than 0 means it kind of implies you non-orientability, and Mobius strip is non-orientable. Okay. So therefore that kind of conjecture came to mind. Might be true. Okay. So our job was to see whether it occurs actually. So this is the diagram. You can see the blue triangles. How many blue triangles are there? How many blue triangles, dark blue triangles are there? 4. How many saddles, villains are there? Black. Sorry, I should have colored black. It's red. Okay, 4. And they are connected, you can see the saddle node connection. Okay. And these are the directions. Each periodic point will have 3 directions because it's a 3-dimensional map. In a Jacobian matrix, you will have equals to Jacobian matrix, 3 eigenvalues. So there will be 3 directions. So therefore there are 3 directions. Okay. You can see 5. So you can see I have marked 1, 2, and 3. 1 eigenvalue, that is here 1, marks the development of the saddle node connection. Okay. 2 might be responsible for the doubling, length double. Okay. 3 might be depending on the classification of the bifurcation. Can be doubled Morgan strip or can be like disjoint loop, like on the cylinder. Okay. So this is the idea so far, conjecture. Here where we come in, to first step into this research, we thought like can we find example which showcase this conjecture at least, okay, before doing. So this is a three-dimensional map, very simple looking quadratic three-dimensional map. X prime is this, y prime is x, z prime is y. How many parameters are there? A and B are the parameters. Just like AC remote, you change the AC remote like the buttons and the temperature goes down up. So A and B are like that. If you change parameters A and B, it might double, it might turn to chaos, it might be periodic orbit, many things can happen. Okay. So for this, when we vary the parameter A, okay, what you do for parameter A on the, see the part A of the picture, parameter A varies from 0.6 to 1.4. Okay, I have varied from 0.6 to 1.4. For each parameter A, I have, in that range, I have length space, like I have categorized in the grid, maybe 100 points or 1000 points can be there. For each such parameter A, I am seeing where the map is. So from at 0.6, you can see there is just a dot. That is like a fixed point. And the dot carries over up to certain point. Then some dust, then some noise is happening, right? Some parabolic noise kind of. That's where possibility orbit is there. Okay, that's where possibility orbit is there. And then you see another period 3. How many period orbit you are seeing? 1, 2, 3, 4. So I'm not able to show. It's not writing up. But after the dust, try to see how many lines are there. 1, 2, 3, 4. Okay. 1, 2, 3, 4. Okay, and then it gets doubled to period 8 orbit. Okay. Right. So this is where we got an idea that doubling can happen. So this is what it looks like if you continue it in a group picture 1.2 to 1.3. Okay. You can see the blue one is the stable one, the black one is the saddle one. Okay. So you can see the blue one has doubled before than the black one. Okay. So if you want to show the doubling case, which parameter should you choose? Around 1.3, because at around 1.3 both of them have doubled already. Okay. Fine. So for that structure I have shown you some snapshots. You can see for the A part, it is like a saddle node connection. Not like a nice loop, but still like a square kind of loop. Okay. The part B represents when the saddle has not doubled, but the stable has already doubled. Okay, the blue has already doubled, but the black has not doubled. The part C, you can see both have doubled at 1.3. Okay, so you can see that it's a length double loop kind of thing, which we were conjectured before. Okay, fine. So when we compute the eigenvalues, you can see the third eigenvalue is less than 0. Okay, so kind of it supports the conjecture so far. Fine. Let us go to the new map. I'm going to be fast because of the time. You can see this is a mirror map. Okay, it's a mirror map. French mathematician mirror. You can see all the parameters of the A, B, and C. Now, what this map gives us? Okay, does it give us the same length double loop or something else? So you can see similar kind of diagram, similar kind of bifurcation diagram. You can see now it is 1, 2, 3, 4, 5. Period 5 orbit now doubles to 10. If you consider this doubling, now let us see. You can see it is a saddle node connection in the part A. In the part B, the saddle has doubled, but not the stable one. Okay, in C, you can see now they have doubled to 10 period 10 orbit, and they have aligned into perfectly disjoint loops. Okay, when you consider the one-dimensional unstable. Now you can at least understand that this structure is actually different from the previous one, which I just showed, the length doubled one. Okay, so these are the two examples of the fundamental and simple example of 3D maps, which show two kind of doubling bifurcation of modular orbits, which was conjecture. Right. And here also you can see when you compute the third eigenvalue, it is now positive. Suppose the conjecture again. Previously it was negative. So yes, so this was in 2023 it was published. After that, I thought like, is the geometry like this? But turns out no. So when you consider some other map like this, you can see it is a modular orbit and completely new topology, like in 3D space. Okay, and when it gets doubled, it looks like that, almost like doubling. Okay, and this map is quite very nice because it is extremely hyperchaotic. and can be suitable for a lot of applications in encryption and cryptography, because these are hyperchaotic sequences, is highly unpredictable. So yeah. So here both kinds of bifurcations you are seeing, both doubling bifurcation of quasi-periodic orbit and doubling bifurcation of mode of orbit in one map. So if you want to do any research, this is an ideal candidate. So this is where you see three. Around 1.2 you can see below part, B part, you are seeing almost three eigenvalue positive. Three different eigenvalue positive. Okay, so that's a sign of chaos actually. Fine. So yeah, so just summarizing. So I have talked about doubling bifurcation of mode-locked orbits. That's our new topic here. I have shown you some explicit examples of birth of length-doubled mode-locked orbits, birth of disjoint mode-locked orbits. And moreover, I have shown you what is the role of doubling orbit to hyperchaos, that is extremely hyperchaotic signals. Okay. So just before we close in, I want to give a challenge to all my youngsters here. So take this example. It's a 2x2 matrix. Okay, this is where I have stuck for 2 years, and I want you to give me some help. So this is some a 2x2 matrix A and B, very nice looking, easy. Okay, all are real entities X, Y, Z, and W. I have observed. This is a result of some research. Okay, this is the boiling after boiling all the things. So if all eigenvalues of A square B and AB square are less than unity, then I have observed that determinant of this AB plus A plus I less than 0 and determinant of BA plus B plus I less than 0 is not possible, or alternatively the last term. Okay, so this is true. I have done a lot of numerical simulation. I have considered millions of parameters for A, B, X, Y, Z, and W. Ran my computer for 2 days, and still I could not find a counter example which can falsify this. So therefore, but I have tried a lot, but could not reach to a proof. So I always give this challenge to my students whenever I teach a new subject in my semester. So a free biryani to those who can help me solve this. Okay. So anyway, let me know. Okay, let me know. Fine. So this is according to NEP guidelines, the flipped classroom model. The teachers are encouraged to give their lectures to students. So you are also my students. So I am giving you the QR code of my lectures, which I teach in the semesters. If you want, you can scan it and get access to them. With that, I thank you all for your kind attention. And if you have any questions,
I can proceed. Students. You once shared this copy to your friends so that you will become low. Any question? One second. Yes.
Sorry, to show that about that conjecture, you mentioned something about like third eigenvalue. How will you labeling that this is first eigenvalue, this is second eigenvalue, this is the third one? How will you do that?
Yes. So let us come back to our. So we can imagine the saddle structure. Okay, so I have labeled 1, 2, and 3. So if the saddle node connection is formed, okay, that means the unstable manifold should reach the stable orbit. If we assume it to be formed, okay, the first eigenvalue should have modulus less than 1. Okay, in your 3 eigenvalues, you will see in your numerical simulations, one eigenvalue will always be less than 1. Okay, and then you label it as 1 because that makes you the saddle connection. That makes the saddle connection. What you label it as 2 because it is a doubling, right? Period doubling. Okay. According to a theorem, period doubling happens when you reach an eigenvalue, when eigenvalue crosses -1. When eigenvalue crosses -1, you see a doubling, like period 2 orbital you get to period 4. Then when the period 2 bifurcates to period 4, when you test the eigenvalues, one eigenvalue will cross -1. That is like period doubling bifurcation. So if you see in those 3 eigenvalues, one has crossed -1, you mark it as 2. So now since we have marked 1 and 2, the only label is 3. That's how we label it. But so far there is no clear-cut labeling like this. You have to memory see and label.
Thank you.
But so far, this conjecture has not been proved. I also request if anyone has visions of how it can be proved, it is nice we can discuss.
My guidance will be higher. Then I think it will be more complicated with the dynamical system.
Yes, I think it will be okay because the curve you are seeing, the red curve you are seeing, is representing a one-dimensional unstable manifold. Such kind of structure we are seeing is a one-dimensional curve. Such one-dimensional curves are unique. There doesn't exist for the same parameter, same system. There doesn't exist another curve which will give you that structure. Only one and one curve, unique curve. That is a one-dimensional unstable manifold. Okay. So when you suppose go to four-dimensional map, suppose let's go to four-dimensional map. So you will have four eigendirections, four eigenvalues, four eigendirections. So in that also you will generate the same one-dimensional manifold. You might see in a slice, in a three-dimensional. If you take a slice, you will be in three-dimensional space. Yeah, you have to take a slice and see. You can't see exactly the space. This is the minimum space where you can visualize this. Yeah.
So this labeling part, when you go to four-dimensional, then it will be even more difficult, right?
Yes.
Even if you see it goes below -1, there what criteria will come?
Yeah, when it doubles, that is the same idea holds, but you will be able to mark lambda 1 because lambda 1 will form the loop. That one-dimensional loop we can mark because that loop will only form if the stable orbit has eigenvalue less than 1. Yeah, so that's the theorem for that. So lambda 1 we can mark, and because it is doubling, you can mark the second eigenvalue because it is doubling raised to cos -1. Okay, so lambda 2 you can mark. You will face confusion in marking lambda 3 because there will be two more eigenvalues, lambda 3 and lambda 2. That's where it might be failing. Yes. But this is where we say that a rich theory has to be. This is just the first example to show that this indeed can occur. This indeed can occur in these examples. This was previously conjecture. So there are lot of research can be done in this area actually. Like first of all to prove this conjecture. Second is to prove this in higher dimensional maps. Like can it occur in higher dimensional maps and how to number the eigenvalues and all those things. Like a proper theorem is remaining. But yeah, we will collaborate and see.
I think the connection to the factor, like Julius factor.
Yes, so the first slide I showed you. So the first slide, let us go back to the first slide. So this is the example of perfectly fractal. Yes, that's very nice. So let me go to that. Yes, so you can see the background of this slide here. So it is like the tops. Okay, in between two tops, suppose green and blue, you see a pink top. Okay, in between a pink and a green top, you see another top. In between any two tops, there will be another top. Okay. So for students, I like to say, if you want to visualize this, go to aloe vera. Aloe vera you must know. Aloe vera how it spirals. In between two big aloe veras, there will be tiny aloe vera. Okay, which will grow and become big. When it becomes big, then in between that there will be another aloe vera. So like a spiral structure and golden ratio is coming. But exactly this is the fractal structure we are talking.
Each stage there will be area in the same.
In each color it is same. In each color it is same. In green color it might be period 6 orbit. In blue color it might be period 5 orbit. Yes, and you can predict in between the two terms. You can predict what is the period. That is like a sum. It is popularly known as Faraday's sum. Faraday has discovered this structure. Very nice structure. As you zoom in again and again, the terms will appear again and again.
Thank you. I think we have more questions and we can directly talk to Sir after the question. Thank you. On behalf of the organizing committee, I am giving the trophy as a token of love to our research person. Please, sir, take it. just to share the photographs at least after the program. So we will have the next talk. So the next talk will be delivered by Professor Pandey, Professor Pandey. I think he is a well-known figure for our department. Many times we are inviting him for many occasions. So I think we will be busy schedule. He has accepted our invitation. We are organized here you. So I would like to request Professor Pandey as our Column to start his talk. And I would like to request Dr. Satyajit Sahu from IIT Bhubaneswar to share the session. Please, sir.
I will move to our next speaker, Professor Pandey from ICPAM-2025. Sir, he is PhD from IMC Chennai in the year 2012. And during his PhD tenure, he visited some research institutes like ISI and some foreign institutions. And after his PhD, he joined as a visiting faculty at CMI Chennai from 2015. And after that, he again joined as a postdoctoral fellow at HRI from 15 to 16. Then he joined as another postdoctoral position at IIT Bhubaneswar. At that time, I was a research scholar at IIT Bhubaneswar. I know earlier. Currently, sir is working as an associate professor at Department of Mathematics at Parampur. In number theory group, people are working basically on analytic number theory and algebraic number theory. Sir is basically working on algebraic number theory and published some recommended journals like Australian Mathematical Society and Journal of Number Theory, Conjecture Journal of Number Theory. And today, sir will talk on the topic prime geometric functions.
Thank you, sir. First of all, I thank Professor Dana for inviting me to give this lecture here. And yes, I have been to Colombo University several times, and I will be happy to have association with this department. I work in algebraic number theory, and my research is also in algebraic number theory, but more or less I will not bring algebraic number theory today, because idea is that I want to tell you a research problem, and a research problem with which I am associated. So I will mention a research problem. I will also on the way mention what is its importance, why it is very important problem. And then at the very end, I will mention that what is my contribution to it, and that will use a bit of algebraic number theory, which I am not bothering to define what it means, but maybe at that stage we will see whether we can do something to introduce that concept. All right. So, and if you have any question, please raise your hand in between. I will try to answer. Am I audible to everyone? So, all right. What I want to talk about is prime generating functions. So, prime numbers you all know. This is at the most elementary level possible, right? Even for a school, this can be defined. So, an integer is greater than 1 is called a prime number. If for any positive integer a, whenever k is a divisor of n, then k is either 1 or k is n. Okay, that means it has no other divisor. Every number has usual divisors, that number as well as 1. The number is prime if those are the only divisors. Alright? There are other definitions of prime numbers, but keep it, we are happy with this one definition. So why primes are important? That is, the first illustration comes by unit factorization theorem. What that says that every natural number bigger than 1 can be written as a product of primes in a unique way. So whatever natural number n you have, basically it's made up of some primes. So primes are building blocks of all numbers. And if you go to the development of number system, you will realize integers are built from natural numbers. Rational numbers are built from integers. Real numbers are built from rational numbers. So in some sense, primes are at the base. They are special type of natural numbers which kind of are responsible for everything. Though when I am making this comment that the primes are at base and the whole number system, from primes you can build all natural numbers at this level, then integer, then rational number, then real number, then complex number. When I am making all this comment, there is a lot of tricky things happening already. There is addition, there is multiplication, and there is some sort of analysis that when you go from Q to R, you talk about things getting closer to each other, right? So all these are there, it's pretty complicated. So prime numbers, they are very old concept and they appear in several areas which we come across. Many of you already might have come across, or if not, you will come definitely, you will see this in future. For example, there is coding theory, there is cryptography, finite fields. Finite fields, I am sure that you must be doing studying in MSc. Then there is local factors of L functions. L functions are some sort of series which are very important series in number theory. There also we have time number secondary. Then there is any equation. How many of you know about Fermat's last theorem? Have you heard of Fermat's last theorem? Pythagoras theorem, I am sure you must have heard. So Pythagoras theorem says that if x, y, z are sides of a right angle triangle, then x square plus y square equal to z square. If x, y, z happen to be integer whole number, then we say that this is a solution of a Diophantine equation. For example, 3, if I take x equal to 3, y equal to 4, z equal to 5. 3 square plus 4 square is equal to 5 square. Same way, I value can be 5 square plus 12 square will be equal to 13 square, and so on. That's several. Instead of that square part, you get 3. Can you find whole numbers x, y, z such that x power 3 plus y power 3 equal to z power 3? Can you do that? Of course, you should not take any one of them 0. If I take x equal to 0, then I take y and z to be same. Of course, it will be satisfied, right? So I want non-zero. Can you do that? No, you cannot do that. This was conjectured by Fermat sometime in 1640s, and it was settled by Andrew Walsh in 1994. After 350 years, and that one problem was responsible for several new areas of mathematics, in particular algebraic numbers. So this is what I mean by this is a big area, solid equations, local global theory, etc. All that. This local global theory is a nice theory, but that failed for Fermat. And these areas like coding theory, cryptography, these are areas that nobody else is able to take your money or nobody else is able to track your message. Okay? So all these are nice applications of science, but actually I'm not going to talk about these applications. I'm very sure maybe some faculty from the department and I see some colleagues from the East, they can give talks on that. And you see, creating a crypto system is pretty easy. It requires very basic number theory. It doesn't require very high. There is a deep number theory, but creating a crypto system does not require deep number theory. And you might see some news like a WhatsApp takes it's very proud of that way. Even they themselves cannot see the messages which their users are communicating, right? WhatsApp keeps like a end-to-end encrypted message. So that claim is because of this, they use a crypto system, and there is a good amount of elementary number theory in the background. So to say that you can devise a system in theory, of course there is a implementation part which will require electronics, etc. But in theory that okay, here is an algorithm to make a communication system, how to communicate between one person and another person, how to make effective communication. The theory part is pretty easy. However, once I devise or I propose such a communication theory that okay, this is the way to communicate, I have to convince everyone that okay, this is a secure communication, right? Otherwise, why will people download that app? To convince that yes, it is a very secure app, that requires huge amount of deep number theory. So I just say crypto system is not where I am going to talk about, but I just mentioned you some basic steps of crypto system. So this is one of the most pioneer crypto system, RSA, named after the initials of the inventor. I think his name is Samir, is Agreement. There is a very nice story. They were having a drink and they were continuing this discussion. It's after some drink they came up with some idea that okay, maybe we can use an elementary number theory. So what do they do? To generate a crypto system, the first step is generate two large prime numbers. Okay? So come up with two large prime numbers. And when I say two large prime numbers, I mean that you cannot say that 101 is a prime number. That's large. No. You have to give me a prime number which has some 500 digits. So just try by pen and paper. I'm sure that you cannot come up with a prime number which has 20 digits by pen and paper. So what I'm asking is for 500 digits. So once you generate, so this is basic number theory, right? Generate two large prime numbers. Yes, it's little involved because it's 500 digits I'm asking, but it's basic number theory. Steps are very clear, right? How to test a number is prime or not. 10 is prime or not? No, right? You take 2, divide it's divisible by 2. 2 is neither equal to 10 nor equal to 1, so it's not a prime number. So it's easy to test whether a number is prime or not. Only it will be more involved. Too many steps if the number is large. So generate two prime numbers, that's pretty easy. Okay. Then again use some basic number theory to generate what is called a public key and private key. Now, public key, private key, one can define that once I have generated these two prime numbers P and Q, I will take their product, and you remember that group theory. Suppose that product of P and Q I call N, then I will look at Z mod LZ star, the multiplicative group modular N. What will be the order of that guy? En, Euler-free function. So use all this, and that one of the number now starting from PQ you will call, generate two more numbers. One you will call public key, one you will call private key. Public key you will publish on your page. You can communicate it to everyone, like a mobile number you give it to everyone, right? So public key you share with everyone, private key you don't share with anyone. And now again some basic number theory used in this public key to encrypt the message. Suppose I have declared my public key is known to each one of you. You want to send me a message, the moment you are typing that message in your WhatsApp, actually this algorithm is encrypting it. And when I want to say once the encrypted message comes to me, nobody is able to see it, okay? People can hack my things and can see possibly the encrypted message, but they don't know what this encrypted message is, what does it mean. Only once I have this private key, people can will know the using that private key. The moment I put my password, private key gets activated, and I see the message which was sent. All right. So very simple. Building a crypto system is a very simple application of prime numbers. Let's start with two large prime numbers, generate a public key and a private key, then use encryption, basic number theory like group theory which I mentioned, Z mod and Z star, Fermat Little theorem. You all studied BSc third year, I believe, right? And that is enough to do the encryption, and that is also enough to do the decryption. All right. So this is something I already mentioned that WhatsApp or your net banking, they all have in background one of the crypto system working. They are automated with our password, our mobile number, so we don't realize what is happening there. As I said, that the moment I enter my password, things automatically are decrypted. All right. So we don't realize what is going on in background. We only realize that if somebody sent me a message. How are you? The person typed, how are you? The how are you traveled all the way, and I have seen how are you. No, it doesn't happen that way. That how are you was converted to 0010000 and things like that. That is what traveled. What way it was converted, you can use just simply a dictionary between alphabets and numbers, and then numbers to binary numbers. That is not effective. That's the after that you apply crypto system, then it becomes secure. All right. So that's a very basic thing about the application of numbers, prime numbers. Now I come to, as you saw that to build a crypto system, what is the first step? Generate two large prime numbers. My talk is about prime generating functions. So I am just going to talk about this first step. What are prime? Can you find? How to find large primes? So you all know that there are infinitely many primes, right? You will prove this maybe close to I think 2,300 years back. There are infinitely many primes, and it was proved in 2,300 years back. But much after that, in 1837, Dirichlet proved that every arithmetic progression, that means if you have whole number a and you look at b plus d, a plus 2d, a plus 3d, a plus 4d, more or less every such arithmetic progression will have infinitely many primes. When I say more or less, I hope you are paying attention. For example, if I take a equal to 2 and d equal to 4, will it contain infinitely many primes? A equal to 2, D equal to 4, then A plus B, A plus 2D, A plus 3D, A plus 4D, A plus 5D. Will that contain infinitely many primes? No, right? Every number in this arithmetic progression is divisible by 2. So only prime number in this is just 2. That's what I meant by more or less. That A and B should be relatively prime. They should not have any common prime. Alright? Whenever A and B are relatively prime, then the arithmetic progression A plus B, A plus 2D, A plus 3D, all these numbers you take infinitely many. There are infinitely many of these are primes. And for example, I will mention 3k plus 2. Here I am taking 2 equal to A equal to 2 and D equal to 3. So 2 plus 3. Alright, so these were the first item is about there are infinitely many primes, there are infinitely many primes in arithmetic progressions as well. But our task is to generate primes. Can I find a faster way to generate large and large primes? So let P and denote the nth prime. Can we find a formula for P? How many of you? Please be honest. How many of you have tried to find a formula for nth prime? How many of you have tried? Please raise your hand if you have tried. best student. At least once in your life, you should like spend 2-3 days. Okay, let me find the formula for prime. Please, you still have time. You have to. I think. I mean, I'm sure that most of your teachers, if you ask, but in my BSc, they were like, today I'm very close to find a formula. But of course, next day I didn't know I wasn't close. But again, I will try and fail, try and fail. You also keep trying. You will fail, but it's okay. Alright, so please do that. Can you get a formula for n prime? That means here is, for example, it is n square plus pn minus 4. That is my n prime. Can you say that? Don't know. Right? Anyway, here this is not good. Let's ignore that. So we want to find a formula for n prime. Alright? What happened after tremendous amount of work by these legendary? The first mathematician I have named is legendary, and I was about to say legendary mathematicians. So these are the pioneers of mathematics: legendary, Gauss, Dirichlet. Over the works of 50-60 years, they said that okay, we are not able to give you a formula for n prime. I cannot tell what Pn equals to exactly, but Pn is in this interval. Take n log n. N is still told to me, right? I want to find, let's say, 100 prime. 100 I know. So look at 100 into log 100 minus 100 by log 100. Then 100 into log 100 plus 100 by log 100. This is an interval that will contain my 100 prime. Okay? After tremendous amount of work by several mathematicians over the effort of some 60 years, this was found. But remember that this interval is of length n by effect 2n by log n, right? And you can calculate if your n is 1000, then how big that will be. Fine? So this is still like a lot of work needs to be done. I said this was believed. I didn't say that they proved this. It was believed. What previous speaker mentioned, that conjecture, based on several feelings, etc. They conjecture that n prime should die in this interval. Okay? They could not prove it. But it was proved eventually in 19th century by Harima and Poisson and actually Poinslow. And it goes under the name of prime number theorem. And if you know, there are certain problems called millennium problems. There are 7 problems mentioned by Clay Mathematics Research Institute. If you solve any one of them, immediately you get $1 million from them. Immediately. And in fact, $1 million they will give you. You are going to get several $1 million. It's that one agency will give you $1 million. I'm sure India, if you saw, the Indian government will give you maybe $1 million, US government, several funding agencies will award you. So, Riemann hypothesis is one of those millennium problems. I think yesterday one of the speakers was mentioning at some point zeros of complex polynomials. Remember? So, Riemann hypothesis is about zero of complex function. I won't call it a polynomial, but a complex function. It says that it's zero or somewhere on a straight line in complex plane. If you solve it, in fact, the Riemann hypothesis, I am sure that your award will not be restricted to $1 million, it will become $1 billion for sure. Almost like a 25% of number theory, 50% of computer science relies on Riemann hypothesis. So it's a big problem. Alright, so that was about importance of primes. Alright, you have any question? Now we go to a function which possibly takes prime values. So prime derivative, as I said that simple, here I am saying that a surprise The reason is why I wrote that a surprise, because somewhere I wrote finding a formula for n prime. I said it looks impossible, right? But here is a formula. This is not for n prime. It says that. So a theorem was proved by somebody that there exists a theta in R such that if I take the function gn equal to theta power 3 power n, theta power 3 power n, that will be some real number, right? It need not be an integer. Then I take the largest integer before that real number. That is called floor function. This bracket which I have not completed, that is actually notation for floor function. This number will be always prime. That was proved sometime I think in early part of 20th century. So, but what does it say? It says that there exists a theta. What is theta? We don't know. So, possibly there are several thetas, but we don't know one theta. Okay? And also you see that these primes are going to become very large and large. For example, suppose, just for example, take theta equal to 2. Theta equal to 2 is not the right choice, by the way. But take theta equal to 2. What is 2 power 3 power 1? What is g of 1? 2 power 3 power 1. 8. Very good. What is g of 2? 2 power 9 you have to do, right? 256 I believe. So already what is g of 3? That is not trying to calculate g of 3, right? So it's very quickly increasing function, but anyway we don't know what theta is. So yes, this would have been very nice had we known that okay, this is the right theta. So yes, it is a great result provided if it provides a right theta, then actually for practical purposes it will be a remarkable result if it gives a right theta. For example, for cryptography, I just need a 500 digit prime number. Okay, take n large, you will get a 500 digit prime number. But you don't know what the theta is. Previous slide I mentioned about Riemann hypothesis. If you assume Riemann hypothesis, then you can calculate theta up to few digits. You can calculate theta up to few digits. For example, in the Riemann hypothesis function has found that you can theta equal to 1.306377 and so on. This large number. See, I hope you see the problem here. If you say, if somehow by chance theta turns out to be a rational number, you will be much happy. Otherwise, see, this decimal places may be after 100th power. If I don't know 100 decimal places, I will have error. That will not give me a prime number. Therefore, this formula actually is not going to help. Even though it's a formula what we were looking for, but it's not going to help because of this possibility of theta, that the theta will compute up to maybe 10 digit or maybe 15 digit. But when you take its 100th power, this number will start giving. You have missed after 11th digit onwards, you have ignored, right? That will give you error when you take 100th power. So you will possibly the actual 100th power was supposed to be ending at 1, but this because of this error it is ending at 5. That is certainly not a prime. So this formula doesn't help. This is I just said this is prime Gn is a prime, but it is not H prime because it's much larger than H prime. This I will skip. This was another formula. Actually, this was I had a stop for 1.5 hours. There is one more formula, but again, eventually I will show that the formula I can easily do that, and that generates all the prime. The previous formula was like it generates some large prime, not all the prime. But this formula which I am skipping, that generates all the prime. But eventually I will show that this is also useless formula. So no need to discuss that. Come back. our target is still the same. How to generate large primes, right? We are still with that question. How about polynomials? Suppose I give you a polynomial, that a polynomial in one variable with integer coefficient, and I say that this polynomial always takes prime value. Will that not be easy? Evaluating a polynomial is easy, right? So if I give you a polynomial that it always takes prime value, life is much more easy. But can we do that? Can we find a polynomial fx equal to a0 plus a1x where a i's are all integers such that f of a is prime for all a in natural numbers? For the time being, let us take a0, a1, a2, a n to be positive natural numbers. We can take negative and then you will say that sometime value will be negative, etc. All that can be handled now. For the time being, let us take all of them to be positive and then f of a is a positive number. We want it to be prime number. Fine? Can we do that? If yes, if you can use such a polynomial, that is my formula for generating not nth prime, but for generating large primes. Good? So let me do one thing. I will introduce a notation. Okay, for any polynomial fx with coefficient in z, we introduce a notation for the all values of this polynomial. I collect all fn as n values in n, and that set I am calling b subscript f. Alright, evaluating all values of f and n. That set all values and calling that collection of all values as my set b f. And the question which was asked for, suppose this bold p denotes the set of all prime numbers, then the question which I asked on the previous slide is this: does there exist a polynomial fx in Zx such that Vfn is contained in P? That means all the values of f are prime numbers. Alright, formulation of questions clear? So does there exist a polynomial f? We bothered about positive coefficient, we keep taking positive coefficient, such that all the values, Vfn is nothing but the value set of f. So all the values of f are prime numbers. Then Vfn is a subset of prime numbers. So maybe you can think about, is it possible? Can you find a polynomial such that all its values are prime numbers? So take any polynomial. I start with there will be any polynomial. I want all its value prime numbers, right? So at least it has to take some prime number, right? If I want all its values to be prime number, at least some value should be prime. So let us begin with that. Suppose f evaluated as n gives me a prime. So f of n equal to p is a prime number. Alright, if f is the right polynomial, then it has to be some prime. Okay, I take f of m equal to p a prime number. But then, what is f of m plus tp? That's also a value of f, right? F of m plus tp is also a value of f. We will show that very soon. I will show that f of m plus tp is divisible by p for each t. But f of m plus c, I have taken all the coefficient positive, right? a0, a1, a2, a n, all are positive. F of m plus tp will be larger than f of m, right? F of m plus tp will be much larger than f of m. So f of m is p. F of m plus tp is divisible by p. Can f of m plus tp be prime? It's much larger than p, but it is divisible by p. So by the first slide, it has a divisor, namely that number 1 in between somewhere p is also there, which divides it. So it cannot be prime number. So our hope will be shattered that we can find a polynomial like this. Alright? So let us do that. So what I need to do, I only need to show that f of m plus tp is divisible by p for every t. That is what I need to do. Evaluate this. Fx is some polynomial, that means it is a0 plus a1x plus an x for n. Then what is fm plus tp? You substitute in place of x, you just substitute m plus tp. So you have a0 plus a1 into bracket m plus tp plus dot 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 plus an into bracket m plus tp or n. Now you expand this. all these brackets, you know, binomial expansion, you can expand it. But I will write it modulo p. Whenever some number is divisible by p, modulo p, you know, right? Congruences. Whenever a number is divisible by p, I will ignore it. So when I expand the very first bracket, a1 into m plus a1 into dp, I can forget a1 into dp because it is divisible by p. So modulo p, f of m plus dp, which is written here, actually equals to just a0 plus a1n plus dot 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 plus an in for n. All other terms will have p in it that I can forget. Okay? And that is what written as the last point. F of m plus dp actually equals to fm modulo p. Good. But what is fm? Go to the bullet number 2. Fm is the speed. So you have a natural number f of m plus dp that equals to p modulo p. So p divides difference of fm plus dp minus p. So p has to divide f of m plus dp as well, right? So you have to do what you wanted. F of m plus dp is divisible by p for p. Alright? Good. So we cannot. First question is, does there exist a polynomial which all its values are primes? We showed that that is not possible. Okay? So it is not possible. Now question 2 we will skip. Now we take a reasonable question. Fine. So are there polynomials which take infinitely many prime values? That's a reasonable question. And are there polynomials which take infinitely many prime values? You recall the result of Dirichlet which I mentioned on the first or second one of the early slides. For example, 2x plus 3. Do you think that will take infinitely many prime or not? Dirichlet theorem which I mentioned, that was 3x plus 2 takes infinitely many prime. Same theorem will tell you 2x plus 3 also takes infinitely many prime. And these are few examples which one can discuss. And okay, so I wanted to explain that if you want your polynomial to take infinitely many prime values, you cannot say that every polynomial will take. For example, 2x plus 4, will that take infinitely many prime values? We discussed in the beginning, no, because 2 will divide every value, so not possible. So such thing we should avoid. And it happened that in 1857, Polynomials made a conjecture that if you start with any polynomial fx in zx with certain conditions, these conditions are more or less what we said about 2x plus 4, that there should not be a fixed number dividing all the values. That is condition number 2. And obviously fx has to be reduced, because if you can write fx equal to f1x into f2s, then f of n will be f1n into f2n, so it cannot be prime, right? So these two are very obvious conditions. And Boolean said that if your polynomial f satisfies these two obvious conditions, then actually f does take infinitely many prime values. This was a conjecture made by Boolean, and currently we do not know anything about this conjecture. Only thing we know, if the degree of fx is 1, then Dirichlet proved this conjecture. Actually, Dirichlet proved this conjecture in 1837, 20 years before this conjecture was made. But if the degree of polynomial is 1, what happens if degree of polynomial is bigger than 1? I will teach you. Alright, so we don't know any single example of a polynomial whose degree is more than 1, which takes infinitely many prime values. Alright? So we don't know anything about this conjecture. Alright? Let us not get into this improvement, etc. So what I did sometime in 2021, I proved that for every prime number L, if you take this polynomial FLX, this is of degree L minus 1 by 2, modulo some very likely condition, this is a conjecture made by me only, that which I said modulo some assumption, that is the algebraic number K. I said I will possibly avoid that. on car we usually take class, but that seems more likely to be true. If that is true, then I prove that all such for every prime number there you define this polynomial of degree n minus 1 by 2. I prove that they do take emphatically prime factors. All right. So that is the result I wanted to share with you all. Thank you.
Particularly is the terms of conjecture number theory. Is there any questions from audience side?
Yes.
Sir, good afternoon. So you now mentioned before the past session that if we take A is equals to 2 and B equals to 4, then the arithmetic progression matrix A equals to A equals to B. And similarly, we cannot find a prime number. My question is that can we use a prime generating function to study the properties of any prime numbers in arithmetic progression?
No. Prime generating function which we talked here, there were few examples. This was one example of prime generating function. This is transcendental example. Okay. What you are asking, can we use it for arithmetic progression, that is linear? So no. The one which I was talking about this at the very last slide. Okay, so I think I will be very fast. This one is a polynomial of higher degree. So coming back to degree 1. Okay.
Thank you.
Any questions? If not, let's thanks to the speaker.
The amazing talk. The next talk will be delivered by Professor Cosmological, PIT. And I would like to request Professor Swabhiswar Parisa to Colombo to share this. Please, sir.
Thank you, sir. Now I would like to invite Professor sir to give the lecture. So about Professor Sir, he has completed MSc MPhil and PhD from Cosmological University. After that, he has visited also 2 countries for his research, research, Taiwan and Mexico. And also he is visiting regularly to different countries for his collaborative products works. And he has published more than 55 international journals in good journals also. And there is also good citations also. There are some papers I am looking for more than 200 citations. Okay. And he is also a 2022 June outside home. He was a top 2% scientist. It is recommended by Elsevier. As I know it is. He is also associated with many as a senior member, editorial member, and any editorial board member, like Springer Lecture and Francis Douglas. Okay. In these few introductions, I would like to invite Professor Sir to deliver.
Students, how are you right now? So, I think here I'm visiting regularly and many seniors doing their research work or PhD work in JIT, disciplinary and other institutes. Some are calling me for motivation and how to start their research. And some are ongoing analysis students from here, they are also contacting me how to improve their work in the future. So, yes, this is one recent topic that is related to sustainability. Any industrial framework, that is implementation of a circular economy approaches is from supply chain models. So we have to check here whether our approaches is correct or not. Which are approaches? Circular economy. So circular economy is very new topic. Due to this new word, we introduce, me and my students introduce the circular economy. For that two words, 3 theses submitted. Okay, within 3 years. And students have been with me 8-9 hours per day. So these words, different new words required nowadays for good research. So earlier, people know only the linear economy. Yes, so researcher that already completed, I think, in Susam in Singapore. I told that you forget about the linear system. Think about and comes to the circular economic approach. Definitely you get some good work or good publication. Now he is doing. I saw yesterday he has posted some, the presentation of. So that is related to circular economy. So how it works? So I am working as an assistant professor, senior grade 2. It's very nearer to associate professor. And they will give within 3 months they will give the associate professor. Not easy to get the higher grade in a very good place. So this is my outline, and the middle two big titles are some case study, or you may say these two are some recent development circular economic models. We tested and we justified our approaches, that is circular economic approaches is 100% correct. Now thereafter I will show you some reference and I will show you my recent activities. Okay. So this is the inventory, that is some goods, semi-finished goods or raw goods, that is a definition of inventory. And types of inventory, there are many types of inventory. Then I have here 4, but still these 4 are traditional inventory. Raw materials inventory, work in progress inventory, finished good inventory, and MRO. Okay, maintenance, reworking, and operations, good inventory. So you may find these 4
concept from any book. So I am not going for more to say about the definition of this book. So basic terms required, that is demand word. Okay, demand and term is very known term. Production rate, shortage quantity, demand and shortage not meet equal that time shortage occur. Then around quantity is an item. Okay, what you are order, that is your item. And defective rate. In manufacturing time, when item produced that time some defective or some damage or semi-damage product will appear. Okay? So this is the defective rate you can find over about D. Then now they told you the general limit, that is when to order and how much you order. So under EOQ model, you can find this picture from any book like Antiso, equal to order quantity. Okay, that we see total cost equal to KD by Y plus XY by T. There are to go for faster derivative with respect to Y, and there are to go for second order. If the second order greater 0, then you take your necessary condition and equate to 0 for finding the Y star is optimum Y. Okay, optimizing of Y. That is optimizing of your order quantity. Okay, so K is the ordering cost, H is the holding cost. Then we have just I told you previous slide what how to find ordering quantity by considering the derivative or partial derivatives. Okay, if one variable, okay, ordinary. If more than two variables, partial derivative. That is classical technique. And for verification of your model, you have to go for numerical technique to validate your model. Then, if your model is very complexity, okay, complex problem, then you go for meta-heuristic algorithm. Yes, and I told my student, use if your system is very complex or higher level, you can find the solution by your classical mathematical way. Then you go for a genetic algorithm or particle swarm optimization. Only for solution purpose, not for not for the comparison, GA, PSO, then other method, then you check this my new algorithm and we have a good result. That is only for comparison purpose. But your model should be new. Okay. So you know the concavity convexity theory. If you are going for the classical model, and you can go for the mathematics. Okay, concavity and the convexity. Okay, you know the SL matrix. Now I move to your supply chain management. That means it. Okay, you can say from produce the item. Then that item, how is it going to your buyer? That is what the in between nodes from manufacturing to buyer. If you connect them, then you get the chain. That chain for the supply chain. Yes. Now I move to the previous one is the supply chain. Still it is old. Still it is old concept. Management people, industrial engineering people are doing. Next, I added another, that is sustainable supply chain. How the model is more sustainable? Okay, globally, locally, as well as globally, your model is appropriate or not. Okay, this is a carbon cap. There are carbon cap and trade policy. You have already two industries. One industry and A and a B. Which industry produce more emission? Industry A. Yes. Okay, like Bhushan. Sorry. Okay, industry A and industry B. We have two. The company and industry having any more emission and industry B less means less emission. Okay, that dotted line, that is the maximum emission. Suppose if you are above that line, then you have to pay cost or money to the government. So industry will having less producer, less emission, therefore, okay, some subsidy or some motivational cost you will get from government. Yes, yes. Therefore, that money or cost is shared to the market. That is, who will purchase? Who will purchase? Now, industry will purchase that extra money from industry. Here, that is called as carbon cap and trade policy. Okay, we introduced that concept in our work. Now, okay, to reduce the emission, green investment required. Green investment is by planting the tree. By planting the tree. And we can use function, but here I use here exponential function. I will say you like green technology investment to reduce the emission. Thereafter, waste is also very important, and it's not good to see. Okay, therefore we have to think about how we use the waste. For that, we consider some function, exponential function, e to the power minus something, I will say. Okay, thereafter I told you, don't go for only linear way. Okay, here so linear economy will not give you the profit more. Therefore, we think about circular economy to reduce the waste, reduce the emission, reduce your all around the things. Okay, therefore, that cost we can add our model, but the cost is not more effective. Okay, if we are add for that 1,000 rupees, our benefit is more. Yes or no? So, circular economy is very important in industry. Recycling, design, retailer, consumption, collection. Okay, okay. This circle, okay, we move always up to what time you can say? Up to get less emission, less wastewater like that. Okay, will not go for zero. Still some emission will come. Still some waste will come. So will not go for zero waste or zero emission. We reduce the emission and waste. Now, scope. What are the scope? I already mentioned you. If you use circular economy approach, definitely industry will get more benefit. So, one model we have developed here, that is integrated sustainable production model for bio-yarn industry. Already 90% is paper work over. We are trying to submit
good journals. Okay? Yes, it's related to banana tree. You know banana? Yes or no? Here, banana. हम लोग खाएंगे आज. Okay? Every conference I am showing some applications. Last time I show here that is related to 3D printing to reduce the waste. Okay, that paper waste. Yeah, here to develop an integrated sustainable model for an exam to maximize the profit while minimizing waste and emission. Now you see this picture. Okay, good now. Yes. Okay, we have here manufacturing, remanufacturing, and here banana farm in the bottom. Banana farm. Okay, after banana producing, that banana, okay, banana will, okay, sells. But what about they are waste? Yes or no? Understood? Clear? So, we collect this stain. That stain means that yarn manufacturing. This side is manufacturing, this side is remanufacturing. Okay? And yarn manufacturing produce from some the cloths used fabric. Thereafter shaping, thereafter blending with the virgin fiber like that. Then spinning, then okay, after spinning again some yarn. Okay, yarn coming retailer. Okay, then customer used cloth. Okay, then we move from yarn manufacturing that side. Okay, so this one will repeat until they less waste. So this use also water treatment also and wastewater. Okay, this design up to wood zero waste and zero waste to water. Zero waste to cannot reduce the wastewater and reduce the emission. So you see, these are some function, demand function, and carbon trade function we introduce here. And this is for retailer inventory, and this part is the production, the manufacturing. The top one is manufacturing, and the down one is retailer. Okay, so what we are doing now, I told you two types: manufacturing, remanufacturing, and another retailer. This is the backbone, bones. Okay, this is the structure, and we put in that. Where we put here, you see, we put here, and we connect. Connect means we are both. Yes or no? We are both, and it will come and say. Yes or no? So, this is the heart of the work. And this is the demand we can collect from the retailer, existing work. That is not important. We will solve several times to which researcher doing demand price dependent, demand quality. This is not the honest thing. Okay, quality, price dependent. Then extend this part, that part. That's not a good thing to get a good work. So this is the already existing work, work, the thing. So holding cost, that connection or nodes, holding cost, production cost, all those transportation cost. In transportation cost, emission is there. Then we multiply some function. Then we reduce the transportation cost. Yes or no? And yes, energy cost. Okay, remanufacturing cost. Waste water treatment, that function we create by getting or by finding some existing work. Yes. Then investment cost for emission, that's like told you. Emission cost under city means carbon tax. without remanufacturing. There is a cost under CT means carbon tax with remanufacturing. Okay, I told you we have to multiply this 1.10 is 1.10 and 1.11 is that 1 minus e power something. Okay, so if we multiply that term, obviously commission cost will increase. Okay, you can take another, but exponential function is best one to get the concavity and the convexity easily. If logistic, then your graphics will move like that. You can say our our concavity and convexity is like that. That's right. So these are some costs, and to verify our cost function for finding the solution, we need some mathematical theorem. Okay, and this theorem we can go for the Hessian matrix. Maybe because our function is not bigger. Okay, these are some theorems to prove whether our integrated model is concavity or not. So we collect some data nearby below, and we collect some data from existing pattern to verify our real industry will work for future or not. Yes, that is. So here you see city will be remanufacturing. Okay, that average indicated total profit. Okay, and here average indicated total profit is check. CNT means cat means what? Carbon trade credit policy. So we have here more profit, the right hand side, that is in cap under trade credit policy. So you can got it easily by considering the non-linear function by mathematical we have done to take the rate point, the optimum solution. Rate point is optimum solution. Yes. So we have here in remanufacturing time, cap and trade credit policy time, we have a more profit. That is the one. So young industry can consider our work so that they get their business. Okay. So I think after publishing some people are some industry contacting, but we are academicians and we have no time and we are not going for that is the limitation because teaching institute this is not easy to go and work with them. So this is the sensitivity analysis. If some EW means emission, and here effect of relation of the EW on the emission cost of effect. So we analyze that one. So conclusion already told you. Okay, in manufacturing time and cap and trade cap policy, industry will get more profit. To test circular economic approach, okay, right or wrong, once again we consider we develop a model that is related to smart home e-waste. Smart home e-waste. Okay, so how we reduce the unnecessary part after using the smartphone. How we use some parts of the smartphone. Okay, so we think and we develop this one. Okay, yes. Okay, good. So we have here, okay, two layers. Okay, so one is retailer and one is the manufacturer. Here we enter secondary market. One professor told yesterday related to secondary market. Okay, your mobile phone got, but not super. Yes, that item can send to the secondary market to get the money. So we use here, see So this will work up to get zero waste and zero emission. That is our target. Okay, this picture we made, we develop first and we try to roughly. Yes, and the arrow we develop properly. Okay, and that the chain or the circle when it stop. Already told you when. Okay, it was the west and it was the east. Emission when you think about emission, when your mobile phone problems. That is manufacturing. Yes, and you manufacturing time when your defective mobile phone that time you will send these items to the remanufacturing. Some parts we can use like that. It's not easy because the pointer is not working properly. So you can use our honest part of the smartphone after using. Yes. So because you see, if you go any smartphone repairing center, have you seen the place? That is very, very tough. Yes or no? We are thinking also the waste, e-waste, the satellite e-waste. We are thinking how to develop or create the models. That is very tough because we are looking only environmentally. Yes or no? Not only one application. We are thinking regularly. Thank you. So we have no time. So one side same concept, but my approach how software people approaches in different industry. So that you see XD function we consider that is exponential function and the some calculus, some conditions will work, and for also waste. So we consider another function that is the exponential function here, and this that inventory system already existing, but we add some extra thing those we consider new. So already told you this one is here manufacturing and this one is here retailer. Then we are with our target picture. Which one is my target picture? That has to be. Yes or no? Clear? So we have to think. Okay, create this, create manufacturing, create retailer, and create our application. And how we are. That is a very good. Yes. So these are some cost analysis. No time, sorry, I have no time. And we use here, okay, uniform distribution because we use the defective value. It's not defective, how much that defective. So some probability, okay, probability theory we are here that uniform distribution is 1 fx equal to 1 by b minus a. When b less than x less than okay. So we use this condition for accepted integrated total profit, and we may also look this algorithm to get the cells whether my model or sorry our model is exists or not. So the red line between the G, the green investment and the waste investment, investment cost, that line we have rule of 163.0.9. So to get the point, solution point, digital point, we wait for the counterplot as well as the 3D. Okay, to verify whether our concavity, okay, theoretical concavity as well as the pictorial concavity formula. So here some analysis there, but our result coming more, profit is more if we use the waste investment and emission investment. Okay, so this is my small references. Okay, we use this reference in our work, and this is my target. I always keep target, big target. If you have big, then okay. If not there, then it come down. Yes, big. Target should be big. Okay, ICPAM. Very very top journal. Okay, 9.8. Okay, and 6.7 we have a lot of difference connection. Yeah, and the third one is my own work, PDF work when I was in Taiwan. Okay, so and so the first one also Probabilistic, and the second one related by coding is related to 3D printing. My student, and the second one, third one is my student work. Okay, and also my student work. Okay, student work. This is related to chicken industry. We use there the QR code. Okay, to get the pieces genuine or not. I think that I presented in the chapter of international markets. Yes. So this is related to the AEA algorithm. Okay, related to wastewater and industry 4.8 tire industry. Tire. Yes. Here. And also it is related to satellite that related. Yes. So this is my close girls are of I cannot sit more with them. Therefore, it's calm down. It's no that you. Okay. So environment system is good journal, but this is not my target. So and the last one is massive industry published this year. Okay. To know you, means international. If you know internationally, you should work extra. Okay, after 10 p.m. night, you should work like that, so that people will know you. Thereafter your work, they can maybe consider for review process. Therefore, you have to work with the big journals. Here, that is the target. Many things happening. I have no time, I will not tell you. Okay? So, this is my history. The first one just due to monetary issues, we got the top one, we got the ICPAM University. Okay, as ICPAM in Bangalore. And second one is Dubai University from Kolkata. Another planning for Mexico for Kolkata. And these three are okay, doing good, but not so like that. Okay. So my team and big guy I have. Okay, big guy required to get more motivation to get good works. Okay. Here, this is the first one I am going after 29 to work with them, Brazil. After 29 that and okay, I told you we collect some data from you. Okay, this is people will ask me how you validate your work. To take randomly your work, what units? No, you should go and check and try to collect some data. Okay, they will not give you 100% data. You should try and collect. So you should have to slow the chain. Okay, this is very important. Okay, so this is more related about me. Yeah, so I have listed 2% 2 times. So I have Mexico, Portugal, Taiwan, and PhD from South and visited USA, New Zealand, Netherlands, Thailand, and plan to visit Brazil soon. So I have 500 SCI, and degree. So this is my first data and Web of Science data. So whatever you are writing, think if you are working for this, it's a site or not. iteration is very important. Okay, my average is like 54, 55, I think across. But that is now 1750 plus. Yes. So what your department of citation require? Yes. People having 200 papers, but citation under 1,000. What is the benefit? Why you are spending more paper and spending more time for more paper? No need. Okay. So this is the thing. And senior editor, I am working 2 years, 3 years in that first one. Second one, just this year I must think I got this opportunity. This is also, and recently yesterday, day before yesterday, I got a mail from editor to get the opportunity, that lecture. And this is only you can submit your work in my own specialist. It is just here, okay? Here you can submit your work related to discover sustainability. Any related to sustainability, not mathematical. You use sustainability. Okay? So thank you very much.
Very nice presentations and lots of application, practical application in waste management. So participants, if you have any questions, you can ask. Anybody having any questions?
Okay, okay.
It's a nice point.
How do you correlate it better with this mathematics? Simple function that you are taking from exponential function or something like that.
So actually, sir, yeah. So we multiply whatever the function, exponential function, logistics not good because sometimes coming like this coordinate, you cannot say this point is continuity or direct letter say. So exponential we are translating, and every nodes we are getting some cost. Okay, every nodes we are having cost that are stored, and that cost multiplied with demand or quantity. That's it only. Multiply only demand cost and ordering quantity. That is not it. But we need to structure, okay, the application structure and the existing manufacturing and retailer, the picture I shared you, that we can put and add them and I put it in the application. But every nodes we are having some costs. That cost related to demand multiplied with demand and ordering demand.
My point is that it's a kind of assumptions that you are thinking of.
Yes, I
But in reality, there will be some other.
yes,
many disciplines will be there.
yes. So this is only assumptions. Okay, this is it. The many mathematics function or the terms we use, that is assumptions. That assumptions and already some existing papers they used. That assumptions is practically working with the model or not, that we are doing. That assumptions, demand assumptions, price assumption, whatever assumption, emission function, that assumptions working on theory as well as theory, numerically and practically. Okay, but that development, that case study picture should be designed by us, me or you also. It's not very hard to get the application.
There must be some gap.
Gap is there. Gap, so we can add some here. I told you that banana yam, I can add some what? Sorry, related to blockchain technology. blockchain to get whether the banana is in correct or not or accurate or not. That banana where it is produced. That banana is produced or not. That you can use. Okay, that blockchain technology you can use it every one. So gap is there, limitation is everywhere. Yes, I'm working in own ideas, but I told you your application, his application, her application should be different. And what you are working your paper, that paper similarity less than 9. Okay, otherwise I will not take the paper. That's it. Whatever you want to do. Yes. That picture I made not 30 hours. No, publish. Afterwards, they have to publish. That
Thank you, Professor Umar. So let us thank him. Department of Constitutional Law Constitution to Professor Umar.
Dear students, if you try and connect with me, if you are going to work research in Belo Horizonte, they are paid 40,000 per month for full-time research. So I am sure if you come, then I will try to stay another 3 years or 2 years. Okay, I am minding some Odia people. You know all are from other states. That is my weakness. Thank you very much.
And the next talk will be delivered by Professor Conjecture, Policy Academy of Sciences, Poland. So he is ready to deliver the talk through online. So, okay, I'm just inviting you to join. Just wait. Am I audible to you? No. No sound. Yes, your voice is audible. Yes, your voice is audible. Also, your screen is visible. So I think we will start. Because we have this sound problem. Okay, I'm just starting.
Okay, thank you for the invitation and thank you for inviting me. Seeing Polynomials after a long time and we've seen it after since 2014. So I'll talk about state comparison with reducing system. This is a learned one with Subhash Dave and David. So before I begin, maybe I'll take some time to introduce the objects that I will work with. So gamma is going to be a countable polynomial. And I'm going to associate a sixth algebra with it. So what is a sixth algebra? Just to define it all. So consider H to be a inverse space, and D of H, the projection of all linear bounded maps from H to H. So sixth algebra A, I knew it, and this is a conjunction of elements from D of H, is the vector subspace. It also flows under multiplication. And the norm that is there in D of H, I will start the argument that is there in D of H. Some example is I'm going to associate to this countable group. So what we do is the following. Let us consider N2 gamma. This is the collection of all maps from gamma to C all functions. We just square it. So if gamma is G, then this represents that related that is one. So now what I want to do is I want to define a map from my group gamma to the collection of all bounded linear maps from the N to gamma to gamma. So I need to tell you in particular, lambda s for each group element must be a bounded linear map from N to gamma to gamma. So in particular, I need to tell you what happens to lambda s of J. So lambda s of J must be an element in N to gamma. So I need to tell you what happens to a t point e, and this is just translation. So each group element is casted at each point. And J is N to gamma. So viewed in this way, I can view the group inside V of N to gamma. So I have the image of the group inside there, so I can look at the span of the lambda s as is over by group gamma. But this is of course closer to multiplication, and the adjoint operation is just the inverse. So lambda s star is just lambda base inverse. But this is not close to the law. So I'll just close it to the law. So then it becomes a C star. And the object that I get here, this is what is called the reduced to C star. Okay. So now, what is the problem that we are talking about today? So the problem is about comparison. So in particular, I want to compare any two elements in the C star algebra. So maybe where does this notion of comparison come from? So in matrices, we know what is comparative, right? So for example, if x and y are just any two matrices in N and C, then we know that rank of x is less than or equal to rank of y. If and only we can find some of the matrices S and T, that x can be written as S. So there is a notion of some sort of a comparison between matrices, and that is the comparison given by the matrix. So in C algebra, so can we do a comparison similar to this notion? Because I don't see is also an example of a C algebra. In particular, so this notion of comparison is defined in general for any unical simple C algebra, but I'll not say what those terms are because this will take us a bit away from today's topic. So now let us only focus our attention to this reduced to C algebra that I defined. And then I can say it with the compacts. So this is these are the compact operators on L2 of gamma. And then let us take any two positive elements. So think of them as positive operators. So let B are just positive operators. So we can apply, we say that A is less than equal to B, or sub equivalent in this sense. If I can find some elements Dn in this tensor product, they are not necessarily unitary, but such that real B, real star, when the conjugation and I take a limit, converges to it. And then so now I also have now I didn't say here is that I have a map that is very defined down on the college from the reduced group system to C. And this is what we call a trace. So this is exactly how the trace behaves for the matrix. Trace of AB is trace of B. It's exactly the same thing. The tower of AB is tower of BA for all the AB, the reduced group system. And so now what happens is that we can define the dimension function to associate it with this trace. Corresponding to tau. So the dimension function theta is defined again from the reduced discharge of gamma tensor K plus. So these are the positive operators to R plus of course. And how it is defined is exactly what one thinks of it. So this is exactly the limit as n goes to infinity down of A 1 over n. Just exactly what happens in the matrix case. And now what is notable, this is a fact proven since 1980s, is that if A is sub-equivalent to B, in the sense that I just defined up here, in this sense, then this implies that B tau out of A is less than equal to B tau out of B. This is well, this is not difficult. Now, the question that people wanted to know or ask is the following. Assume that D tau out of A is less than equal to D tau out of B. So the dimension function preserves this inequality. Does this imply that A is sub-equivalent to B? And then we said, so this is what people get told to be the definition. So reduced group C star algebra gamma. So is it worth telling everything in terms of the reduced group C star algebra? This is defined in terms of integration C star algebra. So, but I'll just stick to this. A strict comparison. If D tau out of A less than equal to D tau out of B implies that A is sub equal to B, and this must happen for all A in the reduced system. So then of course it became important to understand why such groups have the strict comparison property. And this is proven in so this notion, we say this notion was introduced by Blackadar, post Blackadar in 1989, and then it was proven by Dykema and Rogram. This is 1998. So it took them 9 years almost to show that the reduced group C star algebra F infinity has strict comparison. So what is F infinity? So let me say what is a training member. So this is the free group. Or any n generators. So you can use that infinity many generators. And how is it defined? So think of again A1, A2, and AN. And how is it defined? You consider all possible words. So this is basically the collection of all words that can be made from A1, A2, AN. So we can think of like unused inverses. But then what you do is if there is a reduction that is possible, then you reduce it. And then you reduce it to the most, like the least reducible number that you can. For example, here's an example. So for example, I can call the word A1, A2, A3, A3 inverse, A4, A2 inverse, and then A1. Now this is a word, but this is not in my group because this is not reduced, because I can reduce A3 inverse. So this will become A1, A2, A4, A2 inverse, A1. And this is a word in my group. This is an element in my group. And this is exactly what the group consists of, that all possible reduced words that are there. And diagram programs is so that if you consider that infinity the word the group that can be generated as a free group from infinity many generators, there has this strict comparison problem. And if it is satisfies this dimension function, satisfies this inequality, then A and B are combined. And then almost implicit in their discussion, they have this question. Does CR star FN of strict comparison problem? In particular, if I consider the assailant for any equal for any equal. And this was posed in 1998, and until now, until this point in time, people try to solve it, people wanted to know if this can be done. And this was explicitly asked by Robert in 2012 in one of his ICPAM talks. And then this is exactly what we proved recently with Sebastian and David. So this is the joint work with so we proved that if gamma is a countable group, and add some assumptions of course, plus rapid decay, and then define what that means, but you have to take one mark for it. And then it has asymmetrical neighborhood group. So in particular, every group is an example of asymmetrical neighborhood group. And has treated animal right. If the group satisfies these assumptions, of course, not it can be group general, then the group gamma has strict comparison. Then the reduced group system has strict comparison. So in particular, we follow that the reduced group system has strict comparison. For any n bigger than 1. And so this basically we answer this question is positive in this thing. Now maybe I can just take a 10 more minutes. So I take a few moments to explain what is this. The asymmetrical neighborhood is defined. But rapid decay just means that If you there is this group gamma, look at this group ring that we can do. So this is what is called the group ring. And this is all possible solved from the form AS lambda S. And these are all, this is like S is an F and F is a finite. So this is what is called the group ring. So what rapid decay just means that you can see the rapid decay means that if you look at the elements that are supported in the group ring and look at their log, then the log can be counted uniformly in some sense. That's what rapid decay means. That it goes decay is rapid, is exactly what the exponential problem. And what is trivial amenable radical? So we can define what is an amenable group on that. So gamma is for amenable. If since I'm working with a company group, if you can find the sequence Fn connecting a finite subsets from my group, so these are all finite, such that if you look at SFn and you do the delta connection with Fn, so this is basically all the elements that are in SFn but not in Fn, and then all the elements, even the elements which are in Fn but not in SFN. So SFN is just translated of Fn by S. Look at the number of elements here. You write down the number of elements in Fn. And you let limit that and go to infinity. So this possibility for all cases that will come. An example of the third group that all finite groups. If you see that this is the case, all abelian groups. For example, G, these kind of integers, this has this property. You can maintain that the Fn in this case is just from minus n. And you can easily check that it satisfies the set of property. Now, what is a non-example? So, non-example, for example, is not an abelian group, is free group, like I said, the group that I defined is not equal to 2. We can even look at Fn and G for n greater than equal to 3, even 2, because 2. These are all examples of groups which are not abelian. Now, what is an amenable radical? So, they show that every group, this is Jones lemma kind of argument, contains a maximum unique with one maximum normal amenable. So, in every group there is a unique maximum normal amenable circle, and this is what is called the amenable radical, and we denote it by I. So, for example, if you consider an example first, if you consider the product of two, like F2 times G mod integers, then in this case, the amenable radical is exactly this piece. So, G1 G is the amenable radical. Because it is practice number. So, under these assumptions, we were able to show that the reduced basis algebra has strict comparison property. Now, what is the main idea? Maybe I have 5 minutes to say what is the main idea behind the proof. So what you do is that, so U is an orthogonal vector. So these are the big subsets of N. Now, given this group gamma, we can define gamma u to be the product, the infinite outward product of the group gamma, and we work out by these elements, by the diagram. So, gamma u by definition is the all those GMs such that you can find some element in one vector such that G is in gamma such that there exists some G in gamma with Gn equal to G for all elements. So particular means you can find a big subset of them such that after some point every infinite group is basically a sequence becomes constant. That's it. So now we can embed my diagonally we can embed this copy of my group in this altered order. And the idea for us, the main idea for us was to use that you can embed gamma star T to do the semi-directed tensor product. So it was this is the free product in gamma U. Then this actually gives the embedding at the level of the reduced group system. And this embedding, so this is not something trivial to see, but you need this rapid decay property to get that. And then once you get it, then the proof becomes straightforward because of some. Then you can apply Robert's machine. This is Robert's work on these things to imply that you can do system that are gamma straight. Yeah, so this is the main idea behind the group. Of course, like I said, so as the examples of the groups that satisfy this property, like I said, the three groups are there. Then the hyperbolic groups, these are the three class of groups that generalize the notion of the spheres. And all these groups have these properties, and you can also look at SNG for n equal to 3. These are this property and some related the hyperbolic groups are formed. But there are many examples of groups that satisfy this property, and this is exactly what goes behind. And I think I'm out of time, so I'll just stop. Thank you for listening. Nice stuff.
So, this area has been around the last 20 to 30 years, not more than that. And one of the main topics of this area is talking about graphical models, which is where I think most of my work lies on. So, yeah, I'll talk about the specific problem of structural identifiability in Gaussian graphical models. Alright, so let me just give a brief outline of what my talk will be about. So I'll briefly introduce what I mean by graphical models, and then I'll introduce the problem of structural identifiability and causal discovery in specifically Gaussian directed basically graphical models. And I'll then present a result of my work
which is basically making some extra analysis to solve. And we run this, what the result is we get. We run search algorithm or the degree-driven search on some real data sets, and I'll present some of the results that we got over there. And if time permits, I'll talk a little bit about the algebraic properties of these models. Okay, so what is a graphical model? So what we do is we consider a finite set of random variables, let's say from x1 to xn. These could be discrete variables, this could be normal variables, doesn't matter. The language is possibilities are there. Now what we do is we use a graph to explain the dependent structure among these variables. Now when I say a model, it's basically I mean a collection of probability distributions or also some collection of covariance matrices and you'll see later on that satisfy certain properties that are obtained from a graph. And this also provides also an interpretation of the model, which is why it is being used in machine learning, causal inference, artificial intelligence, and so on. So let me just briefly explain what I mean by causal interpretation of the model. So let's consider four random variables. Let's say. So we have range, slippery roads, interpretation, and let's say car accidents. So if you assume that there is no hidden variables or it's a feedback loop, then the best way to explain the causal relations among these variables is that rain will cause slippery roads, rain will cause interpretation, and both slippery roads and interpretation will cause car accidents. So what it means over here is rain directly does not cause car accidents. That is where there is no direct edge between rain and car accidents. But rather it causes car accidents through slippery roads and interpretation. So that is why we have this causal structure over here among these variables. Okay. So this is like a direct example of what I mean by causal variables. Now, what is the graphical model that what are the properties of the boundary distributions that I just mentioned? So graphical models can be explained by different types of graphs. So it could be undirected graphs, it could be directed acyclic graphs, it could be mixed graphs, and whatnot. But I focus mainly on this directed acyclic graph. And what I mean by that is basically you have a directed graph with vertices B and directed edges, such that it does not form cycles. You have I1, I2, I3, I10, and if it comes back to I1 again, then it forms a cycle. So we want to avoid that. Now, the thing that we use here is called as the pairing set of vertex. So the pairing set of vertex J is basically all the vertices I such that I and J is an edge, right? So this is like very intuitive. Now, when I say the model according to the graph is basically the collection of probability distributions that factorize according to the graph. So you have the probability distribution that factorize according to the graph and the f of xi given the pairing set of x. So it's basically the probability distribution factorizes according to the conditional density. This is basically the conditional density of xi given its pairing. So let me just explain this with an example here. So we have this directed acyclic graph over here, 1 goes to 2, 2 goes to 3. Then the model here is basically all those probability distributions at on exponential speed, such that it can be written as such that it factors in this form. The conditional density of just f1, f of x1, then f of x2 given x1, and then f of x3 given x3. Okay. So this is how we define the model. And there's also the notion of conditional independence that comes from the graph. So graph models can also be described by the conditional independence structure of the graph. So think of it this way, that if the edges correspond to some dependence among the variables, the missing edges kind of correspond to the independence among the variables. So that is where the concept of conditional independence comes from. So generally we say that the variables of xa is independent of xb given xc, and it's denoted by this again the probability distribution function factorizes the distribution. This is not important. This is not a notation to show that how the probability distributions factor. I'll not really get into the technical definition, but think of it this way. So you have two vertices of I shape in the graph, and your f separating and here some set of data. So that's some separation right here. Given the separation set. That's like an intuitive way of thinking about it. Alright, so now that they have conditional dependence, okay, maybe I can explain this in an example. So, as shown on the last one, the toy example that I showed. So, in this example, the missing edge over here is like the edge 1 and 4 is missing here, right? So, we can say that x4 is conditional independent of x1 given x2 and x3. So, graphically, what is happening is x4 is getting separated from x1, x2 and x3. So, this causes separation. Now, what it basically says is that if we have enough information about x2 and x3, then knowing more information about x1 does not really provide additional information about x4. So that is what it means to be conditionally independent. So if you know that the value of x2 and x3, then knowing the value of x1 is not going to say anything additional about x4. Okay? So that is like the meaning of conditional independence in this setup over here. Alright, so now that we have conditional independence, what's the issue in here? So the problem is, two vectors must be marked for equivalent when they satisfy the same set of conditions. So the problem that happens is that you can have two models equal to each other even though the two graphs are not identically equal to each other. Okay? So let me explain this with this example over here. So earlier I said, range causes slippery roads, division, both slippery roads and division causes our accidents. But if you just look at the conditional independent statements coming out of this graph, it is impossible to differentiate between this graph, this tag, and this graph. So, like if we just switch the arrow from rain causing slippery roads to slippery roads causing rain, we'll get the exact same conditional independent statements. So, we know that this is not true because slippery roads won't cause rain. But imagine you have thousands of variables and you do not know how two variables interact with each other. If you just have the conditional independent statements, then it will be impossible to differentiate between this graph and this graph. So it will be impossible to know what is the correct causal relations among certain variables. Because over here, both these graphs satisfy 1 independent 4, given 2, 3, and 2 independent 1. So that is kind of the problem that we face in this situation. That is, if we just have conditional independencies to work with, we cannot differentiate between the graphs that which actually from which the conditional independent statements are actually coming from. Okay. So before I get into what can be done to solve the problem, there's some nice results which allow us to see the structure of these Markov equivalents. So the collection of all tags which are Markov equivalent to each other, or like satisfy the same set of conditional independent statements, we call it Markov equivalence class. And there's a nice characterization of how we can, just from the graph structure, we can say that two graphs are Markov equivalent to each other. So a nice result by some famous statisticians, Berman and Pearl, they say that if GMS and two DAGs, then the corresponding models are equal if and only if G and H have the same skeleton, and the skeleton I basically means the corresponding. Then let's say this fourth one. So the underlying skeleton is basically the unvectored graph, which is x1, x2 is connected by an unvectored H, and x2, x3 connected by an H. So all these four graphs have the same skeleton. And if you look at the V structure, it's basically forming a collider like this. U to V and W to V, but there's no S between U and W. So over here, there's no collider, because you have x1, x2, and x2 going to x3. There's no collider structure. So all these three tags do not have any collider. So that is why they are not equivalent. But for instance, over here, this forms a collider between x1 and x2. So there's an x1, x2, and x3 to x2. So this forms a collider, but these three do not have the collider. That's one equivalence class, and this one lies in one. So, okay, this is one characterization of trying to see when graphs are not equivalent, but this still does not form our problem. So, but since we cannot differentiate between these three tags, just comes under dimensional dependence. Okay, so let me just tell what is generally done in this situation. So, the concept of causal analysis or causal discovery, what they do is, we attempt to infer the tag to which the data generating distribution is faithful. What it means is that you have a collection of conditional dependencies coming from the data, and you want to find out the correct tag. And as I just said, you want to find the correct tag. What's the next best thing that can be done is we try to find out the correct mark of equivalence. Okay? So what is generally done is, with the data interpretation, a typical approach is to subdivide the space of all that into these mark of equivalence classes and explore them using one that representatives of the class. So let's think of it as we have a collection of all diagonals and vertices. You break them into mark of equivalence classes, and each equivalence class has a certain number of diagonals and them. And we use a representative of each of these classes and try to explore them using the data. So there are different algorithms that exist to the mark of equivalence class from observation data. There's something called as the PC algorithm, which tests on the dimensional dependence, really equivalence search, and okay, I'm not getting into that, but certain algorithms exist to find out the mark of equivalence class. Okay, so far it still does not solve how we can actually get into the exact tags, because just from the observation data, we actually get it. So, what more can we do in this setup? So, this brings us to the problem of structured identifiability, that is, if we build graphs just from conditional dependent statements, how do we decide on the tag of questions? Right? So, just from conditional dependent statements, it is impossible. So, what we do is we use some additional constraints. So, there's something called as interventions. We can intervene in a particular vertex and we get some additional data to test on the so that we can get the directions. There's also another concept of some more constraints on the model, which is, we call it as symmetry. So this is what my work is based on, and that's talking about. Right. So my work is mainly focused on the Gaussian representation of the Gaussian graphing of described by the right case. So far this was true for any distribution on the tag. Now I'll mainly focus on the Gaussian. So what we use over here is, for each vertex, we introduce standard variables, let's say xi and epsilon I, where epsilon I is independent from the variables with mean 0 and some variance greater than 0. Now each of these xk's can be expressed in terms of xi's, epsilon i's, and some regression parameters, lambda ij, which is written in this form. That is, xk is, we take the sum of lambda ij and xi plus epsilon j, where the sum is taken over all the payments. So let me just explain this as an example and it'll be clear. So let's consider this tag over here. So the first thing to see is indeed a tag, because there is no cycles over here. If you go from 1 to 2, 2 to 3, have the arrow from 3 to 1, there are pocket cycles, but the arrow is in different direction. So let's look at the parent set of all the vertices. So the parent set of 1 is empty set, because there is nothing pointing towards 1. Similarly, 1 is pointing towards 2 from 1, and so on. Now, using the parent set information, the random variables for each of these vertices satisfy this equation. X1 is just x1, and x2 is, we take the sum over the parent set, so is just has one variant, so x1 times the regression parameter lambda 1 2 plus x1 2 and so on. Okay, so this is how we get the structural equation. This is called a structural equation for Gaussian graphical model. And what we do over here is sort of looking at the probability distribution, so the Gaussian distributions in the model. We can see them, we can identify them by their covariance. And that is precisely what we will do over here. So the model basically corresponds to a Gaussian graphical model. We can think of it as a collection of certain covariance matrices that satisfy certain properties. And these are the nice properties that it satisfies. So every covariance matrix is denoted by sigma can be written in terms of the regression parameter that we saw and the variance parameters omega by this matrix factorization. That is I minus L inverse transpose times D times I minus L inverse. L is an upper triangle matrix, which is, you can think of it as an adjacency matrix. So it has got lambda ij if ij is an edge and is zero otherwise. So let's look at this example, the same example over here. So the D is the diagonal matrix which has got the variance parameters from omega 1 to omega 4, and L is the matrix corresponding to the edges. So you have 1, 2, 1, 3, 1, 4, that corresponds to lambda 1, 2, lambda 1, 3, lambda 1, 4, and so on. So for instance, the X 3, 4 is missing, so 3, 4 can be overlaid to 0. Okay? So basically, the model is the collection of all the covariance matrices that can be written in this form. Alright? Okay, so what do we do? We assume some additional constraints in the model. So we say that, let's assume that variance is for certain regression parameters, the edge parameters, let's say they could be equal to each other. And we represent that by color. So symmetry can be put in the model to achieve structural identifiability. And the way that we do is that we introduce these colors, that is, we say omega I is equal to omega j. If the vertex I and j have the same color. Similarly, the edge coefficient lambda I and lambda j are equal if the edges I and j have the same color. So this was introduced by Stefan Lorentzen, like Polynomials graphical model, but we take that to the direct graphical model system. So some nice results that already exist in this literature is that if you assume, if every data structure environment, if all margins or variances and all margins have the same variance, what it means is that equal to each other, that is, all the vertices are colored equally. How the skeleton look, I'm not going to get into that. But let me just state what we did in our result. What we showed is that if you have all the edge parameters, lambda is equal to each other, even then it can achieve structural identifiability. That is, if you have, we're looking at a graph after equivalence class where all the edges have the same color, then you can actually find out the correct DAG from the equivalence class. So that basically gives you that if you have this direct constraint that the variance and the edge coefficients are equal, then you can actually achieve or then you can actually find the direct DAG and not just the equivalence class. So let me just give a quick view of like how the proof looks like. And as I said, so far it's been statistics, but as I can go to algebraic statistics, so the proof is very algebraic in nature. So what happens is, as we saw the connection between these covariance matrices and these variance parameters and these edge parameters, it allows us to define a rational time factorization. So we have over here, sigma is this product. So what we do is we just map sigma ij to this ijth entry of this product. So that is basically how the rational factorization is defined. So we map sigma ij to this ijth entry of this product. This allows us to view the model as an algebraic variety. And what we do is like we compute the defining equations of the model which is same as computing the vanishing ideal of the mind. So we can actually identify the models by the vanishing ideals. So let me give an example for this. So let's see, let's look at the same graph that we saw. So the parameterization, what it basically does is just map sigma unity IK and here this product. So in particular, it looks like sigma 1 1, which is mapped to omega 1, because that's sigma 1 as entry of this product. Similarly, sigma 1 2 is just mapped to omega 1, that's lambda 1 2, and so on. Now what we're doing to compute the vanishing idea, we're basically computing the kernel of this map. By kernel is basically everything that maps to 0. And when we compute this kernel, we see that this is being generated by this degree 3 polynomial. So yeah, we can identify this modified. Alright. So how does the symmetry help us? So think about it this way. So we have in this example that sigma 1 1 is omega 1. So if you want to write all the omega parameters in terms of what would you do? So you can write omega 1 as sigma 1 1 here, and let's say you want to solve for lambda 1 2. Then you can write it as sigma 1 2 over omega 1, which is just sigma 1 2 over sigma 1. Right? Similarly, if you want to write omega 2, you can solve it from this equation using this and these first two. So what we do is we just find a rational function for each of these lambdas. And a well-known result in this literature is that the parameterization that I just showed is actually birational. That means that for each lambda and omegas, there exists a rational function for which you can actually equate these lambda and omegas. And what we do is actually make use of this relation. So when we said, let's say, okay, it's better to explain an example. So let's look at this graph here. So when we assume 1 and 2 are the same color, that means that omega 1 is equal to omega 2. So what we do is that omega 1 is sigma 1 1, and omega 2 is this rational function over here. So with this added constraint, we just set these two polynomials equal to each other. And we just figure out the denominator to get a polynomial which is a new polynomial that does not exist when omega 1 and omega 2 were different. So using these additional polynomials, we actually test them on the data to find out the direction. So earlier we could not say this direction would have hold, so had it been 2 or 3 or 3 to 2. But now with this extra polynomial, we can actually test on the data to actually say that the edge will be from 2 to 3. Okay, so that's like the overarching idea over here. Okay, so now what we did is using this additional polynomials and like the fact that we can actually obtain probability, we tested some real data set. So there's something called as so we have this specific structure which we also showed in structure 95, that is if two nodes have the same causal effect on another node if or only if it is common sense. So that's like an assumption activity. Now what we did is we ran a 3D equivalence search type algorithm on a real data set of -1. So we have this data set basically consisted of 11 physiochemical properties and it's consisting of acidity, sugar content, pH, and whatnot. And the aim was to model the causal dependent structure among these physiochemical properties, which would help in predicting the overall quality of the wine. And what we did is that we made this assumption that two nodes can have the same causal effect on another node only if it is a common channel. So with this assumption, when we ran our algorithm, we will actually see that the long arrows actually had believable causal meaning. So the first thing was that there was a directed edge from the vertex chlorides to the vertex density, which basically suggests that the variation in the amount of chlorides will actually have an effect on the density of the wine. Similarly, we also saw that certain edges were clustered together and had the same color, and which basically and the clustering was basically the vertex chlorides containing the vertices these the sulfur dioxide, sulfur dioxide, and sulfur. What it basically says is that as these are all chemically related compounds, it could mean that the compounds influence chlorides in a similar way. So all these three atoms, they are in some phase, some sort of some sort of family angle. So they could mean that they have the same causal influence on fluoride, and that's how they could have some common causal mechanism. So that's kind of the outcome of the real data set, the algorithm that we ran on the data set. Alright, so let me just quickly end the talk by talking about some algebraic properties of these models. Now, before I say about the algebraic properties, let me just create a reminder of what I mean by sorry derivative. Let's consider we have an n% matrix with integer entries. Then the ideal derivative noted by ICPAM is basically the ideal derivative by the denominator of the form x to the u minus x to the v, where u minus v is the kernel. So let's explain this with an example over here. So let's compare to this matrix. Then the historic idea corresponding to this matrix is basically derivative by these denominators. Let's look at the first one here. So we have x1, x3 minus x2, x4. So this corresponds to the vector u minus v, where u has 1 in the first and the third position. That corresponds to x1, x3. And v has 1 in the second and the fourth position, corresponding to x2, x4. So if you do a times v minus v, you actually get 0. So that is how you get historic ideas from matrix. And from that, can we characterize the direct acyclic graphs whose vanishing area is actually tonic? So that was basically the problem. The graph which has a direct vanishing area. So some nice results that we have in this direction, not really get into details, and let's take out the results that we have. Is that let's say if we take the arbitrary tag and let's say G prime is a new tag, obtained by adding new vertex tags and making that a sync. Like by sync, I mean that you add edges from the form of I to F, J to F, and all the existing vertices and connect that to F pointing towards S. Then what we can show, the vanishing area of the new tag G prime is correct only if the original tag was correct in the beginning. So this kind of makes you to extend the current graph into a new graph such that the current ideal is being preserved. And the second result was somewhat similar, was that if we have given the two tags with current ideas, then G is basically tag obtained by something called as a C fluid of G1 and G2 as an AND plane. I mean, I'm going to get into the definition. Same fluid, it's a combinatorial definition. Just think of it as you have two tags and you glue them together in a very specific way. Then the vanishing ideal is the new tag is also correct. So the correct nature is kind of preserved after you do this. So alright, so this is basically some bright properties that we are also interested in. And here are a few references. Thank you.
you just allow him. You just allow him. Okay, good morning. So, are you feeling cold there? Okay, minus 2 degree, very tough to survive. Okay. Really, this time we are going to organize an international conference. We plan to invite you as the invited speaker. Okay. I am introducing the speaker, Professor Sanjay Mandar, Fukushima University, Japan. So, I think you can share your screen and you can deliver the talk. Yes. Yes, yes, it is. So I'm just telling. Your sound is good, perhaps. Make it unmute.
Sorry. Now I'm audible.
Yes, yes, sorry. You can share and you can start.
Okay, Zijan. Make your
Good afternoon,
everyone. It is my pleasure to be part of this conference. Sorry. No, you can start. No, you can start. Okay, sir. Good afternoon, everyone. I am Sanjay Mandar, working as a postdoctoral fellow at Fukushima University. And first of all, I'd like to thank Professor Sanjay for inviting me to this conference. And it is my great pleasure to share my research in this conference. And namaskar to all of my gurus present there. And my research advisor, Professor Vindra Mishra. I think he has many things about the modified theories of gravity or cosmology. So everybody must be hungry, so I won't take long time. I will try to finish it quickly. So these are my topic outlines. I will overview slightly about the problem. In the FQ cosmological model, I will discuss how to construct a cosmological model, then to test the model against some observational data, then we see some real life example and summarize. Okay. So as we know, into Big Bang theory, our universe started from a single point from where it boomed suddenly and it started expanding till now. As you can see here, it started from inflation, then after 12 million years, there first star forms, then start galaxy, planets, everything started evolving. And currently, we are in a accelerated expansion phase. And here, those distance increasing because of some unknown force and energy, normally in cosmological term called dark energy, means we don't know about the dark energy. So, through geometrical modification, we are going to see how we can explain this phenomenon of our universe. So, let's observe this accelerated expansion of our universe was observed by two observational groups, which one is led by Desideus and second one was led by Solomon. For their remarkable achievement, they received the Nobel Prize in 2011. So, along with that, at that time, the Lambda-System model we know as the well-known cosmological model, which comes from general relativity, was the basic model to explain the accelerated expansion of the universe. Then what modified gravity? So there is some issue with the cosmological constant we use in the Lambda-System model are still dark energy, dark matter, dark matter is the biggest challenge in the modern cosmos. And there are some many more problems related to general theory of relativity. So now our aim is to modify this general theory of relativity to solve these cosmological issues. So mathematical proposition. Before going to modify the general theory of relativity or when we are going to construct any theory of gravity, we need mathematical proposition. In the simple sentence, which three basic things we need? We needed many things. So in this case, gravitational theories, we are going to use Riemann geometry or non-Riemann geometry. And a geometric structure which will describe the whole structure of our universe. The third one is a connection where there is some change, there is some shift, there is some shift in position. If there is some changing, then with the help of a connection, it is a geometrical structure, we can measure the changes which is happening in our universe. So this connection, differential geometry normally we call affine connection, it has three terms. The first one is called Levis property of the universe, and normally we can say the bending property of the gravitational. And the second one represents contortion, K1. The contortion which represents the twisting property of the waves. And the last one is the non-magnetic tensor, which describes when something is stretching in the length. It will describe those properties. So this connection can describe combining three properties. One is like orbital and bending property, another the contortion which is twisting property, the third one is the stretching property. If we remove these two, suppose second and third term, we will come up with GR, general relativity, where this Q component represents the non-magnetic tensor and the percentage T represents the contortion tensor. And here we consider these two absence of the twisting property and the stretching property only presence of the conventional part. So then we can find GR. Similarly, we can find teleparallel equivalent to GR, where the contortion part we consider the contortion part, the twisting property. And the third one is the symmetric teleparallel equivalent to GR, in where we keep silence the conventional part and the torsion part. So Also, we call these three geometric theory of gravity. These three theories of gravity are fundamentally equivalent. They share the same properties. So, again, so now as I talked previously, we are going to discuss about the modification. So, what if we extend those GR, STGR, particularly, then suppose in GR, if we add some invariant scalars like this scalar which comes from generally, I think probably Professor Hisser talked about, then we come up with FR gravity, FRT gravity, FRM gravity, and these are started so widely to discuss the cosmological properties of our universe. So similarly, again, if we are adding some extra term like scalar, tensor, vector, then we come up with scalar theory, Einstein theory, and many. Similarly, now if we are changing in geometry, then we come with tensor geometry, symmetrical gravity, FG gravity, and FT gravity. And in this theory, in this talk, we are going to talk about FQ theory, which is based on the stretching property of the curve. So, before going to start out to talk about FQ theory, let's talk overview what the gravitational theory built on which aspect, in which model. So, Einstein theory of general relativity is matter is how to curve and curve instantaneous matter how to. In simple example, suppose this is our space-time and it is a rubber sheet and it has a property, it can slip, it can squeeze and it can sink. So, if this is space-time, if we can put something weight on this rubber sheet, the shape of the paper will change. Right? Again, if we move the paper like this side, this also the weight on the paper also you will see. Similarly, the matter and geometry are correlated. So, and to correlate again. So, we need a formula, we need an equation to combine the matter property and geometric property to describe in a single plane. So, here you can see like Einstein equation normally we call it action that represented by S. If you see the first term, it represents the geometry where R comes from the layer. Immanent geometry with the calculate using some metric we can find the values of R, and here before X which is nothing but potential volume, and G is the determinant of the matter. And here if you see the second part which represents the matter. Right? So then comes to the FQ